Hi, I'm Fernando Pereira from UFMG, and today we shall talk about how to produce static program slices traversing the dominance tree. If you remember, a static program slice is given by the backward traversal of the program dependency graph, starting at the instruction that defines the slicing criterion. As an example, these nodes marked in orange are the program slice for the slicing criterion given by label 23. The dependence graph is formed by data dependencies and control dependencies. Tracking data dependencies is very easy. We just have to read the instructions in the program. If we have an instruction that defines variable v and uses variable u, then v depends on u. This is the subslice formed by data dependencies only. Tracking control dependencies is harder because we cannot see them directly by reading individual instructions. We need to reason about which variables are created under the influence of which branches. This figure shows the control dependencies in our example. So the goal of the rest of this class is to identify control dependencies. Again, I'm assuming that you can easily identify data dependencies by simply reading the instructions in the program. So the question is how to identify control dependencies. We shall use this algorithm to identify the dependencies, control dependencies I mean. It's written in SML, but don't worry, you can come back to it and read it later if you want. Instead of explaining each step of the algorithm, we shall illustrate it with an example, so really don't worry about its syntax. The basic idea of the algorithm is to traverse the dominance tree of the program. Whenever we find a node that terminates with a branch, we stack the predicate that controls the branch. Whenever we visit an instruction, if the stack is not empty, we create a control dependence from the predicate to the variable defined by the instruction. No worries, we will start looking into an example now. At any moment, we shall keep a stack with the predicates that we had visited during our traversal of the tree. So for instance, if we are currently processing this path, then our stack will have three elements. These are the predicates that control the branches along this path. So we have a predicate b0 here, another b1 here, and finally a third predicate b2 here in the third branch. We remove predicates from the stack when we find the post-dominator of that predicate. This, of course, is just an abuse of language. We are finding the post-dominator of the node that contains the branch where the predicate is used. We are showing the algorithm in SML, and you can read it later. This is a functional programming language. It might look complicated in the beginning, but the algorithm is rather short. Let's see how it works now. Here's our dominance tree. We start visiting the first node in the tree. At this point, the stack is empty, because we have not visited any predicate thus far, so no dependence is created when we visit the instructions at label L0, L1, and L2. Then we visit the second node of the dominance tree. Because the first node did not end with a branch, the stack remains empty. So again, no control dependencies are created when we visit labels L3 to L7. And now we visit two more nodes. But this time, when we visit the block that contains L8 and L9, there will be a predicate on the stack. It's b0, the variable used at the branch at label 7. We will have to create some control dependencies then. We use this code to create control dependencies. Again, you can read it later, or stop the video to read it now if you want. The important thing is that it creates dependencies from the predicate on top of the stack and the variables defined by instructions. We will see with an example. So we have two instructions to consider, one at L8 and another at L9. The former defines a variable p0, the latter defines a variable len0. We create dependencies from b0, the predicate on top of the stack, to each one of these variables. That means that we are adding two control dependence edges to the dependency graph. We continue traversing down the dominance tree. Now we visit the block that contains labels L10 to L14. We add dependencies from B0 to all the variables defined in that block. There will be 4 new control dependence edges in the dependence graph. After we visit this basic block, we push B1 onto the stack to keep visiting the block at L15. However, we pop the stack to visit L17 because L17 is the post-dominator of the current block. So upon visiting L15, L16, we will add two control dependencies from B1 to LAN1 and to P1. But when we visit L17, L18, the stack contains predicate B0, not B1. And then we will add a control dependence edge from B0 to B2. Then we visit the two last blocks. When we visit L19, we will have B2 on today's stack. That creates a dependence from B2 to max 0. But when we visit L20, we will pop the stack, because L20 is the post-dominator of L18. And so the stack will contain B0. In this case, we will create control dependence edges from B0 to all the variables defined at this last basic block, namely max1, sum1, and I1. So you can see on the right the control dependence edges that we have created. Notice that we create them in a single traversal of the graph. Furthermore, each variable can be controlled by a single predicate, which is the predicate on the top of the stack when the variable is defined. But we will account for transitive dependencies anyways, because a predicate can control other predicates. So that was the algorithm that builds control dependencies. Next class, we conclude the discussion on static program slicing. Till there, you feel free to write me with questions and comments. Thank you.